Hi, this is Sir Eldon. Once again, we will be having our sample problems on work and energy. Let's start. Let's start with number 1. You drop a 2 kilogram book to a friend who stands on the ground at a distance d that's 10 meters below. If your friend's outstretched arms are at a distance 1.50 meters above the ground, as illustrated, how much work done by gravitational force do on the book as it drops to her hands? B. At what speed will the book be when it reaches her hands? And C. If the book has thrown upwards with a speed of 2 meters per second, at what speed will the book be when it reached her hands? Okay, so you're the one who's dropping the book. So for a simple illustration, I have this one. Okay, this is for problem number 1. As you can see here, I have here the initial position of the book and the final position, which is 1.50 meters above the ground. Now, this is just a matter of conservation of energy actually. But we have here this question letter A is particularly asking what's the work done by gravity. And for all we know, it is only gravity that is doing the work. Okay? So with that, we have the formula for work, that is just F dot S, the definition of work, or that is just Fs cos phi, wherein it's force times the distance times cosine the angle between your displacement vector and your force. And mind you, our force here is actually the force by gravity, exerted force by gravity. And then this is our displacement. Our displacement vector is actually going down since it is freely falling. Now, there are people that wants to solve this one using only kinematics. Yeah, we could use that one. But it is also important to note that our lesson is work and energy. And mind you, conservation of energy or using the concept of energy in solving this problem is actually easier compared to kinematics. Okay, so going back, we now have this work. Since we're after the work done by gravity, so that is just work done by gravity times the force of gravity times the distance the book traveled times cosine phi. Now, so that is just basically mg times the displacement or distance times cosine phi. Now, mg, that's just 2 kilograms times 9.8 meters per second squared. And then the distance that it traveled, it is coming from 10 meters y1 going to y2, that's 1.50 meters. So getting the difference between them, you'll get 8.50 meters. So the distance that it will travel is 8.50 meters times cosine 0. Why 0? Your displacement is pointing downwards, okay? And your force of gravity is also pointing downwards. The angle between them is equal to 0. Hence, cosine 0. So the work done by gravity now is 166.6 joules or 167 joules. Okay, so this is now our answer for letter A. But there are people who wants to answer this one just by using the potential energy or the gravitational potential energy, wherein we had this one. The work done by gravity is just equal to the negative change in gravitational potential energy. Change, that is final gravitational potential energy minus the initial gravitational potential energy. Hence, we have this one negative times u grav 2 minus u grav 1, or that is mgy2 minus mgy1. Since common see mass and times gravity, so we have here mg, then times y2 minus y1, that is our y2 is 1.50 and our y1 is still 10 meters. So we got negative 8.50 meters for that one. This one, 1.50 minus 10 meters. So we got negative 8.50. So the work done by gravity using this equation, that concept, it will give us 166.6 joules or 167 joules. that's our answer for letter A. We have two methods actually, and these two methods will work whether in different problems or in this problem. Either of the two solutions are acceptable. Okay? So that's for letter A. Let's have letter B. At what speed? I'm sorry for that dog. For letter B, at what speed will it reach the hand of your friend? Okay? So this one, we have to understand that the one that is working is only gravity. No one's exerting any work aside from gravity. So we will still be using this 167 joules or that 166.6, wherein we got this idea that work done could actually alter or change the kinetic energy or change also the speed of our particle that is moving. Okay, so what will happen is that since work is just equal to the change in kinetic energy, so we have 1 of mv2 squared minus 1 of mv1 squared. By the way, these are just speeds, those are not velocities. Okay, so work done by gravity now is just equal to 1 of mv2 squared minus 1 of mv1 squared. Common factor 1/2 and m, so I'm just factor them out. So v2 squared minus v1 squared. And what is the value of v1? v1, it is basically telling us that our book is just being dropped, so meaning our speed is just equal to 0. So v1 is just equal to 0. So we are left with 1/2 2 kilograms v squared, wherein that is equal to work done by gravity. Since we only have v2 as our unknown, using algebra, we could have this final working equation. That is, v2 is just equal to the square root of twice the work done by gravity over 2 kilograms. So we now have this answer. That is now equal to 12.91 meters per second or 12.9 meters per second. It will reach the hand of your friend at a speed of 12.9 meters per second. Okay? And then for letter C, by the way, iba pa pala. For letter B also, we could solve it using conservation of energy. I have this another another method if you want. So you have there the initial point and then the final point, this one. You have point 1, the initial, and then point 2, the final. Okay? So at the initial point, since it is just being dropped, you don't have kinetic energy. You only have gravitational potential energy at that point. And then as it falls, that gravitational potential energy is decreasing and is being converted into kinetic energy. Energy. Since our reference point is the ground, that is our y is equal to 0. So at this point, this is 1.50 meters above the ground, we still have kinetic energy there. And we still have gravitational potential energy also there. Okay, so it is being shared as gravitational and kinetic energy. So using conservation of energy, U grav 1 will just be equal to U grav 2 plus kinetic energy 2. Or we can have this one. This is the complete conservation of mechanical energy. We don't have K1. We don't have elastic potential, obviously, because we don't have springs yet. We don't have work done by other forces. And at point 2, we have kinetic energy point 2, U grav point 2. So U grav 1 is equal to K2 plus U grav 2. Since we are only after the speed, we have here K2 equal to U grav 1 minus U grav 2. So that's 1/2 mv2 squared equal to mgy1 minus mgy2. I want to divide both, to multiply both sides by 2 over m. Hence, I will be having this equation. V squared is equal to 2gy1 minus 2gy2. And manipulating that one, we could solve for the speed at point 2. So we have the speed now that is equal to 12.91 meters per second or 12.9 meters per second. It is just the same with our method number 1. It will still give us the same answer. Okay? So either of the two, I will accept the solution. But just be careful what is being asked. If it is in terms of if in terms of kinematics or using conservation of energy, be mindful with that one. It's kind of tricky also because we could actually solve this using kinematics alone. Okay? And lastly, we have letter C. Instead of just instead for the book just being dropped, what if you have thrown it upwards at a speed of 2 meters per second? So at that point, at initial point, it's still the same. The ground is still our y is equal to 0. So at the initial point, you have both gravitational potential energy and kinetic energy because you initially you have thrown it upwards. So you have kinetic energy. And then as it travels down, you have still gravitational potential energy and kinetic energy. So what will happen now is that you have u grav 1 plus kinetic energy 0.1 is equal to u grav 2 plus kinetic energy 2, or we have k1 plus u grav 1 equal to k2 plus u grav 2. We are after the speed at the hands of your friend, wherein the rich will book at that point. So that's from k2. So you have 1 of mv2 squared equal to 1 of mv1 squared plus mgy1 minus mgy2. Using algebra, we now have this working equation. Substituting our values, we have v2 now, this is equal to 13.06 meters per second, or that is equal to 13.1 meters per second. That is now our answer for letter C. And as we have predicted also, or as we have learned also, that if something is being thrown at a certain speed, we expect that at that point, at the same elevation with respect to letter B and letter C, is that it should speed up. Hence, our V2 at the point of the hands of your friend is that it is greater than the V2 that we have solved in letter A, because we initially we have given it initially a kinetic energy. Unlike kanina, our kinetic energy wherein it's just being dropped, K1 is just equal to 0. But this time, K2 is K1 for letter C is not a 0 value. It has a value 1 half mv1 squared. Okay, so our answer is 13.1 meters per second. So that's our answer for example number 1. Okay, let's have number 2. By the way, sorry for the resize of the video. Sige, let's have number 2. This is kinda easy lang. A particle of mass m, 5 kilograms, is released from point A and slides on frictionless tracks as shown. Determine A, the particle speed at points B and C, and lastly, letter B, the net work done by gravitational force as the particle moves from A to C. Okay, by the way, I just have another notations for this because as shown in the figure, it's presented to us in terms of letters, in terms of A, B, and C. Point A, B, and point C with different elevations. But basically, they're just the same if this is 1, this is 2, and this is 3. It's just the same. We just have to analyze this by 2 points. Okay, so let's have letter A. We are asked about the speed of our particle at point B and then point C. Okay, pwede natin itong i-analyze. We could analyze this one from point A to point B, from point A to point C. Pwede din naman, or it could also be from point B to point C, whichever you like. But for us, it's better for us to analyze it from A to B and from A to C. Okay? Just remember, this energy will always be conserved here. So regardless, at any point, we should have the same energy. Let's have letter A, the speed at point B first. Okay? So at point A, it's purely gravitational potential energy because it started from rest. And then as it reached point B, that gravitational potential energy is being shared. Okay? It is being divided into gravitational potential energy at this point B, and then it becomes into some of the gravitational potential from A is converted into kinetic energy. By the way, this should be kinetic energy at point B. Ayan. So, with that, we have gravitational potential energy at point A is equal to gravitational potential at point B and kinetic energy at point B. Or basically, we have this one. This is from conservation of mechanical energy. And there is no work done by friction. So work others is just equal to 0. So we now have this. Substituting our formula, we have now 1 of mvb squared equal to mgya minus mgyb. Using algebra, we now have this equation. Yan. And then, we find Vb. So the speed at point B, by substituting all of our values, we have 5.92, we have Vb that is equal to 5.94 meters per second. Okay? And for letter C, for the speed at point C, I want to analyze it from point A to point C. So U grav A now is just equal to U grav C plus Kc. So with that, we have this one. So U grav A equal to Kc plus U grav C. By the way, this is still coming from conservation of energy, conservation of mechanical energy. Doing algebra, as shown, our speed now becomes 7.67 meters per second. As you can see here, it is actually the same with our understanding that as it goes down, our particle is speeding up. Diba? So as it goes down, the kinetic energy is getting higher and higher. Hence, our speed here is 7.67 meters per second, which is higher than our 5.94 meters per second. Letter B. Find the net work done by gravitational force as the particle moves from A to C. So our concern now is what is the work done by gravity as it moves from A going to C. Not from B to C, not from A to B, but from A to C. And as we have seen, this is a frictionless. And as we are just asked about the work done or the net work done by gravity. So, work done by gravity is just equal to the two ways. We could have it the change in kinetic energy from A to C. We could also have that as negative change in gravitational potential energy. Either way, our answer will always be the same. Let's start with this one, wherein gravitational potential energy, or the work done by gravity rather, is just equal to the change in kinetic energy. And then the kinetic energy at point A, our initial point, is just equal to 0. This is 0 actually. We're asked about, or we are just to solve the kinetic energy at point C. And that is 1/2 times mv squared, wherein we have solved this already. So that's 1/2 times 5 times 7.67 meters per second squared will give us 147.07 joules, or work done by gravity is 147 joules. Positive, because our displacement is going down, is pointing downwards, and our force done by our force by gravity is pulling it down. Okay, so the same direction, angle between them is 0. So it should be doing positive work. Hence, we have positive 147 joules. The other way is also, we have this one, work done by gravity is just equal to the negative change in gravitational potential energy. The change in gravitational potential energy from point A going to point C. So, you have negative U grav C, final gravitational PE minus initial gravitational potential energy U grav A. So, doing algebra, we now have this one. The work done by gravity now is just equal to negative times 5 times 9.8 times 2 minus 5. It will give us 147 joules. So what the work done, or the net work done by gravity, is just equal to 147 joules, which is consistent with our first method. It will just give us the same answer. Let's have number 3. Number 3 is, I think, kind of long, but it's just easy. A 2 kg block is attached to a spring of force constant 500 Newton per meter, as shown. The block is pulled 5 cm to the right of the equilibrium and released from rest. Find the speed of the block as it passes through the equilibrium position if A, the horizontal surface is frictionless, and B, the coefficient of friction between the block and the surface is 0.350. So you have two scenarios. So first is I want to illustrate that one. This is my illustration. This is the original or the relaxed state of our spring, wherein it is at equilibrium, wherein x is just equal to 0 meters. And then something pulled it to the right. Okay, so giving our spring an elastic potential energy. It has the potential to do work now. So at that point, we are full of elastic potential energy. And then upon release, it is being released from rest. Hence, we don't have kinetic energy here. Released from rest, the spring will always want to go back to its original state, which is the relaxed state. So, it will now point, or it will now move going to the right. So, as it moves to that equilibrium position, it still has energy, right? So, it has kinetic energy here, wherein our spring is not stretched nor compressed. So, at that point there, as it passes through that equilibrium position, it is always full of kinetic energy. So from elastic potential energy, it is being converted into kinetic energy. Okay, we have different scenarios here. For letter A, what if there is no friction? Okay, what will happen? So if there is no friction, there is no work done by other forces. So it's purely elastic potential energy is just equal to kinetic energy. Okay, also please be mindful, our stretching distance is given in terms of cm, so it should be in meters. Just take a look at your constant K, that's 500 Newton per meter. It is in Newton per meter. So it is understandable that our stretching distance or compressing distance also should be equal to, should be in meters also. So if there is no friction, elastic potential energy is just equal to kinetic energy. So doing algebra lang ito lahat, we now have V2 is just equal to the square root of kx1 squared over m. Okay, this particular formula here, this square root of k over m, this is very vital for us in terms of oscillation. This form will always go back and will be repeated again and again when we go to oscillations. So, substituting our values, the speed now as it passes through that equilibrium position, the box will have a speed of 0.791 meters per second. Now, for letter B, what if there is friction? So there's something that is doing, there is some other force that is doing the work, which is the friction. So work others is just equal to the work done by friction, wherein work done by friction is just equal to Fs cos phi. Our friction force is just equal to mu, coefficient of kinetic friction because it is already moving, times the normal force. How will we get the normal force? Then we have to go back to FBD, when summation of forces y is just equal to MAY, wherein AY is just equal to 0. Hence, this is the FBD of the box. Normal force minus FG. So, normal force is just equal to FG or equal to MG. Hence, our F now is just equal to MG times the mu times mg, and then substituting it here again. Hence, we have this formula. F is equal to mu mg, and then work done by friction is just equal to mu times mg times s times cos phi. What's the s? That's our distance, the stretching distance. Not the stretching distance, but the distance from the stretch spring going to that equilibrium position. It will travel 5 cm or 5 times 10 raised to negative 2 meters. And then the angle between our displacement and our friction force is 180 degrees. And our mu, the coefficient of kinetic friction, is 0.350. So since there is that work done by other forces, what will happen now is that it is now equal, this elastic potential energy is just now be added with work done by other forces, or work done by friction is just equal to K2, or basically this one, mu L1, elastic potential energy at point 1, plus work done by other force or work done by friction is equal to K2. Doing algebra and substituting our work done by other forces, we now have this one, this final equation, wherein we will be substituting all of our values here. So what will we be expecting for the speed is that it should be lesser than what we got in A. We got a 0.791 meters per second. So we will be expecting lesser than that 0.791 meters per second because we have work done by others. We have the work done by friction, and friction opposes motion. So the speed now is equal to 0.673 meters per second. It will now agree with our understanding that if there is that work done by other forces, especially of friction, our speed will always become lesser. And comparing it if it is frictionless. Okay? So that's for example number 3. It's for letter B. Let's now have number 3. Let's now have number 4. A 2-kilogram piece of wood slides on a curved surface, as shown. The sides of the surface are perfectly smooth, but the rough's horizontal bottom is 30 meters long and has a kinetic friction coefficient of 0.20 with the wood. The piece of wood starts from rest 4 meters above the rough bottom. A. Where will this wood eventually come to rest? And B. For the motion from the initial release until the piece of wood comes to rest, what is the total amount of work done by friction? Let's have the illustration. We have this illustration here. So, this is our rough surface sa bottom. That's 30 meters. And this is the curved smooth surface. So, from the top, at point 1, it will slide down. Over here. Now, as I have said, in analyzing conservation of mechanical energy, it is better for us to have 2 points. And it is up to you how to locate those 2 points. I have drawn this one here, that box, because this could also serve as our as another point, wherein we could have this as point 2 and this one as point 3. But it is also safe that we will be analyzing it also from point 1 going to point 2, because the danger with point 1 going to this point, let's have that as 2 asterisk as that point, because we are prone to errors actually, and we have to find first the kinetic energy here or the speed here, and then analyze it again from this point to asterisk going to this point, so that we could get the distance wherein our wood will come to rest. Okay, so but I will just analyze it coming from this point going to that point. At this point 1, it is started from rest. It has started from rest, so it's only V1 will just be equal to 0, so no kinetic energy here. And then it is only full of gravitational potential energy, wherein if this is our reference point, U grav is just equal to mg y1, wherein y1 will just be equal to 4 meters. Okay, so it will now slide down going to point 2, wherein going to point 2, it will eventually come to rest. V2 will just be equal to 0. And then there's no gravitational potential energy here because y2 is just equal to 0. So what happened to energy at point 2? Well, most probably it has been dissipated through heat, or it has come to rest because there is that friction. There's that work done by other forces. There are other forces doing the work, doing negative work, which slows down or slowed down our block, giving it a kinetic energy at this point actually equal to 0, or speed now is just equal to 0. So we have here the rough surface wherein mu k is just equal to 0.20. We will not be using this 30 meters. Why? Because it is not totally at that 30 meter point at this end point here that it will stop. Because we are asked here where at that point from the initial point of our rough surface going anywhere to the right of the curved surface, and that it is not 30 meters. So it must be something. So what will happen is that we will be analyzing it from point 1 going to point 2, wherein work done by friction is being made. So what will happen? Still the same. We have the work done by other forces. We have this one. Work others is equal to work done by friction, Fs cos phi. F is just equal to mu Fn, wherein Fy, we have this free body diagram. Fy is equal to May, Ay is 0. So Fn is just equal to mg, or Fn is just equal to Fg equal to mg. Work done by friction is equal to mu mg s cos phi, where phi is just equal to 180. Why 180? Because our displacement is going to the right and our friction force is going to the left, going against the motion. So 180. It's doing negative work also. So S is unknown because we do not know at what distance the friction is doing the work. Okay, but what we know is that it will eventually stop at this distance here. So we now have this conservation of mechanical energy. So there's no kinetic energy at point 1, only gravitational potential energy. And work done by others, there's the work done by friction equal to 0 because there's no kinetic energy, gravitational, or elastic potential energy. Okay, so U grav 1 is just equal to work done by friction. So substituting U grav 1 and work done by friction, we have this equation here. And we are ought to find this value, that S. So S now, doing algebra, we have this. S is equal to negative y1 over mu cos phi. So that's negative 4 over 0.20 cos 180. So the S now is 20 meters, or the distance that it took for our box to travel and then eventually stop is 20 meters. And then at this point in our rough surface, somewhere here, or let's have this here, wherein it will now have a speed of 0. It has come to rest after traveling 20 meters from the starting point of our rough surface going there. Okay, so that's our answer for letter A. For letter B, what is the work done by friction? Okay, so the work done by friction, so this one, it's just, we have to go back here, this, wherein we will just have to substitute S. So we now have work done by friction is equal to Fs cos phi mu mgs cos phi. It's 0.20 times 2 times 9.8 meters per second squared times 20 times cos 180. We now have work done by friction that is equal to negative 78.4 joules. It should be doing negative work because it has stopped the motion of our block. And also, if you want to check, this work done by friction should actually be equal to the gravitational potential energy here at point 1. Okay, so if you want to check mgy1, that's 2 kilograms times 9.8 times 4 meters. It will actually give you 78.4 joules. And then conservation of energy, it will eventually equal to 0, satisfying this equation. Okay, so that's our example number 4, the last example for work and energy. I hope you have understood the problems thoroughly.